Welcome students to the MOOCs course on fuzzy sets, arithmetic and logic. This is lecture number 27. If you remember, in the last class we started fuzzy quantifiers and in today's class I shall continue with that. We know that fuzzy quantifiers are of two types. One is a first kind, that is number type, and other is the second kind, which is proportion type. And we were discussing first kind, and we have looked at propositions such as there are q i's in some set I such that Vi is F, where F is a fuzzy set and Q is a fuzzy quantifier of first kind. And the example that we studied was there are about 10 students in this class with low attendance. In practice, this variable or say this statement may be more complicated. Say for example, suppose we write P is there are about 20 students in this class whose attendance is low, but performance is good. So, it is a more general version. We have one fuzzy quantifier. We are looking at essentially two different fuzzy sets which give attributes to the students. One is attendance is low and the other one is performance is good. So, to obtain truth value of P, we can write P as follows. Let me call it P prime, that there are about 20 low attendance and good performance student in the class, and therefore, again as before, we need to find scalar cardinality of a set E, where E is the set of students with low attendance and good performance, since both are fuzzy sets, we look at mu low attendance of x and mu good performance of x for all x in the class. Therefore, scalar cardinality of E is equal to sigma over x mu low attendance of x and mu good performance of x, which is equal to sigma over x minimum of mu low attendance of x and mu good performance of x. Therefore, if we can define these two sets and we can compute the membership value for each student to both the classes, by using this summation we can get the scalar cardinality of E, and once scalar cardinality is obtained, truth value of the proposition P is equal to mu about 20 of cardinality of E. This part is very similar to our earlier example. So, I hope that you understood how to solve a problem of this type. With that background, let us now focus on fuzzy quantifiers of second kind. Example: about a quarter of the students of this class are B.Tech students. Given a class description, we can obtain truth value of the above statement. P. Suppose the class has 100 students, of which 28 are B.Tech students. Therefore, for all x belonging to the class, we define a set B.Tech as follows: mu B.Tech of x is equal to 1 if x is studying B.Tech, 0 otherwise. Therefore, cardinality of the set E, where E implies B.Tech student set, is equal to sigma over x is equal to 1 to 100 mu B.Tech of x is equal to 28. Now, suppose the fuzzy quantifier about a quarter is defined as this set that is about a quarter is a fuzzy TFN 0.2, 0.25 and 0.35. Therefore, truth value of P is equal to mu about a quarter of 28 by 100, because that is the proportion of student who are studying B.Tech is equal to mu about a quarter of 0.28, and by the definition that we have given, mu about a quarter of 0.28 is equal to 0.7. Therefore, truth value of the above statement can be determined as 0.7. Let us consider slightly more difficult scenario. Suppose the proposition is almost all the young students of this class are performing well. And we want truth value of P given certain facts of the class, and suppose we have the following fact: student age mu young x marks mu good of marks and minimum of these two columns. So, suppose the facts are the students are x1, x2, x3, x4, x5, x6, x7, x8, x9 and x10, and suppose their ages are 24, 22, 32, 25, 23, 22, 24, 28, 23 and 30. And suppose the marks obtained by them are 80, 85, 75, 68, 72, 90, 80, 72, 68 and 90. Now, to obtain these two columns, we have to define the fuzzy set young and the fuzzy set good performance. Suppose we define them as follows. The set young is defined with a membership like this, that is, young is a trapezoidal fuzzy number with 18, 20, 22 and 26. And suppose good performance is defined as anybody above 80 is membership value 1, and between 60 to 80 we have a linear function like this. Therefore, good performance is a half TRFN, which is of the form 60, 80, 100, 100. With these two fuzzy sets defined like that, let us now fill in the above table. So, membership of 24 to young is half, membership of 22 to young is 1, membership of 32 is 0, membership of 25 is 1 by 4, membership of 23 is 3 by 4, membership of 22 is 1, membership of 24 is half, membership of 28 is 0, membership of 23 is 3 by 4, and membership of 30 is equal to 0. Similarly, for good performance, membership of 80 is 1, membership of 85 is 1, membership of 75 is 3 by 4, membership of 68 is 0.4, membership of 72 is 0.6, membership of 90 is 1, membership of 80 is again 1, membership of 72 is 0.6, membership of 68 is 0.4, and membership of 90 is 1. Therefore, now we need to look at the minimum of this, because we are looking at both young as well as good performance. Therefore, we look at the conjunction of this, and therefore, by standard intersection or by standard fuzzy t-norm, we are using the minimum. So, this is half, this is 1, this is 0, this is 1 by 4, this is 0.6, this is 1, this is half, this is 0, this is 0.4, and this is 0. Therefore, scalar cardinality of E is equal to half plus 1 plus 0 plus 1 by 4 plus 0.6 plus 1 plus half plus 0 plus 0.4 plus 0 is equal to 1.5, 1.75, 2.75, 3.25 plus 1 is equal to 4.25. Now, we need to obtain the proportion of young and good performing student of the class. So, if we define cardinality of E is equal to W, then W is equal to young and good performing divided by number of young, which is equal to 4.25 divided by cardinality of young, and that we can find from our table. This is equal to half plus 1, 1.5, 1.5 plus 1, 2.5, 3.5, 4 and 4.75. is equal to 17 upon 19 is equal to 0.895. Therefore, given the fact of the class, the truth value of the statement that almost all the young students of the class are performing good is 0.895. Thus, for the fuzzy quantifiers of second kind, we have the following canonical form. Among the V's in V, such that A1V is F1, there are QVs such that A2V is F2. This is apparently complicated, but let us compare with the example just I have given. This is the set of students A1V is the attribute age, F1 is the fuzzy set young, Q is the quantifier, almost all, and A2V is the attribute performance or marks, and F2 is the fuzzy set good. So, when we have such a canonical form, we convert it into a form like this: Q E1s are E2s, that is almost all young students are good performing students, therefore, E1 is the set young age of V, E2 is the set good marks of V, and we conclude P prime W is Q where W is the measure of subsethood of E2 in E1. Graphically, suppose this is the total class, this is E1 the set of students who are young and E2 is how many of them are good. Here cardinality of E1 is equal to sigma over V mu young of age of V, and cardinality of E1 intersection E2 is equal to sigma over V minimum of mu young age of V and mu good marks of V. Therefore, we can generalize as follows. Cardinality of U1 is equal to sigma over V mu F1 of attribute 1 of V, cardinality of E1 intersection E2 is equal to sigma over V minimum of mu F1 of A1 V and mu F2 of A2 V, and W is equal to U1 intersection E2 upon cardinality of U1. This is the ratio that one can use to obtain the truth value for P. Obviously, 0 less than equal to W less than equal to 1. Now, let us look at inference from quantified propositions. We have seen that all quantified propositions can be written as P W is Q, where W is equal to cardinality of the set E, and for first kind, that is number type of fuzzy sets, or W is equal to cardinality of U1 intersection E2 divided by cardinality of E1 for second kind of quantifiers. Now, the purpose of inferencing is that given n quantified propositions, what we can infer or what can be deduced from them. That is, if we have P1 is W1 is Q1, P2 W2 is Q2 up to Pn, Wn is Qn, and our aim is to find a statement P W is Q, and we try to obtain its truth value. Here each Qi is a quantifier, and each Wi is the cardinality of an appropriate fuzzy set. Now, the generalized version of inference is that if there exists function f of W1, W2, Wn and g of W1, W2, Wn such that W is between f W1, W2, Wn and g W1, W2, Wn, then one may conclude P that W is Q if Q is at least f Q1, Q2, Qn and at most G Q1, Q2, Qn. Therefore, if we could obtain such functions, then we can conclude W is Q. In practice, we use a simpler version which says that if there exists a function f such that if W1, W2, Wn is equal to W and if Q1, Q2, Qn is equal to Q, then we can infer that P is W is Q from the propositions P1, P2, Pn. For illustration, consider these two propositions P1. There are about 100 days in a year when it rains. So, this is a statement with a fuzzy quantifier of first kind about 100, and the P2 is on about half of the rainy days there is traffic jam. So, this is a fuzzy quantifier of the second kind. So, we want to infer P, there are Q traffic jam days in a year. I think the idea is clear. We have some fuzzy quantifier related statement about on how many days there is rain and a proportional statement on how many days there is a traffic jam. So, we want to infer about on how many days in a year there is a traffic jam. We want to have an idea of this fuzzy quantifier Q. So, to generalize this, we have Q1 is equal to about 100, Q2 this is associated with from P1 and Q2 is equal to about half, and this we got from P2, and let E and F be the set of days in a year when E corresponds to rainy days and F corresponds to traffic jam days. Therefore, we have P1 is W1 is Q1, where W1 is equal to cardinality of the set E. Here we are looking at scalar cardinality, and P2 is W2 is Q2, where W2 is the proportion cardinality of E intersected with F, number of rainy days and traffic jam days. Assume that traffic jam causes only with rainy days, then it will be clear, divided by the cardinality of the rainy days. So, this gives us the proportion on how many of the rainy days there is going to be traffic jam. And W is going to be the cardinality of F. We can consider typically we consider F of AB is equal to AB. If you remember, we have stated this, that from the given statements, these are the quantifiers, we are trying to get F, and W1, W2, Wn are the different fuzzy sets defined on the set of elements, in our case the set of days. Therefore, F of W1, W2 is equal to W1 dot W2, and W1 is cardinality of E multiplied by cardinality of E intersection F divided by cardinality of E is equal to cardinality of F is equal to W. That is, this is the number of traffic jam days among the rainy days. So, what we do? Fuzzy multiplication, suppose we have about 100 is the fuzzy set given by the fuzzy triangular number 90, 100 and 110, and let Q2 be about half, which is a quantifier of second kind, is also a triangular fuzzy number which runs between 0.4, 0.5 and 0.6. To obtain Q, we multiply the TFN 90, 100 and 110 by the TFN (0.4), 0.5 and 0.6. This is Q2 is equal to about half, and this is nearly 100. Q1, which is a quantifier of first kind. And this is of second kind. Therefore, 0 plus of q we can easily get as 90 multiplied by 0.4 and 110 multiplied by 0.6, that is the interval 36, 66. 1 q is equal to 100 multiplied by 50, 0.5 is equal to 50. In general, alpha q1 is equal to 90 plus 10 alpha to 110 minus 10 alpha. Alpha q2 is equal to 0.4 plus 0.1 alpha to 0.6 minus 0.1 alpha. Therefore, alpha q1 star q2 is equal to 36 plus 4 alpha plus 9 alpha plus alpha square to 66 minus 6 alpha minus 11 alpha plus alpha square, which we can write it as alpha square plus 13 alpha plus 36 to alpha square minus 17 alpha plus 66. Therefore, if we plot it, we get something like this. It appears like a triangular fuzzy number, but we know that it is not. In fact, it is going to be quadratic equation. So, we can expect a shape like this, and we have already studied that such type of shapes can be approximated by triangular fuzzy number, provided the maximum gap is within a threshold. So, like that we can estimate the value of q. The concept of inferencing from fuzzy quantifiers can be further extended as follows. One of them is called product syllogism, That is, suppose we have proposition Q1 is are F's and P2 is Q2 is and F's are G's. From that we want to conclude by a similar way is Q1 Q2 is are F's and G's. That means, suppose E is the original set and of which F of them is a fuzzy set, and among those which satisfy both E and F there is the fuzzy set G, and we want to infer about G intersection F out of E. Therefore, we can write it P1 W1 is Q1 and this is the proportion cardinality E intersection F of E, and P2 is W2 is Q2, which is actually the proportion E intersection F intersection G of E intersection F. Therefore, we infer W is equal to W1 W2, that is equal to cardinality E intersection F by cardinality E into cardinality E intersection F intersection G by cardinality E intersection F, and which becomes E intersection F intersection G out of cardinality of E. That is, it gives the proportion type quantifier for Q is R F and G. The other type of inferencing is called consequent conjunction syllogism, where P1 is Q1 is RFs and Q2 is and P2 is Q2 is R G's, and we want to infer Q is R F's and G's. That is, suppose we have E of which this is F and this is G, we want to infer about how many of the E's are f's and g's. So, here q is given by max of 0 minus 1 intersection less than mean of q1 q2, where we have defined mean and max earlier. For your recollection, mean is the set A comma B, and membership of Z to this is given by supremum over all Z which satisfies minimum of x comma y, minimum of mu A of x and mu B of y, and mu max A comma B of Z is equal to supremum over Z is equal to max of x comma y, maximum of mu A x comma mu B y. Like that, when we are given different proportion type quantifiers, we can infer about some other statement or other proposition P when we are given P1, P2, Pn, that is n different quantified propositions where quantifiers are of the proportion type. Okay, students, with that I stop fuzzy quantifiers. In the next class, I shall look into a very interesting type of fuzzy inference system, which is called Mamdani's scheme for inferencing, given a set of propositions or fuzzy propositions and an input variable. Till then, thank you.